So you guys have it for note. So what's going to happen, guys, is today we're going to do the lesson, but unfortunately, because of the FSA, you guys will not do the on your own until next week. And next week is going to be kind of up in the air because of testing face-to-face. So if they have me covering classes, then I don't know if we guys will meet. Okay, so you need to pay attention to the daily agenda every day to know if we're going to have class. And if we don't have class, then I will probably post the video or post what you're supposed to be doing. Okay, so you need to definitely pay attention to the daily agenda starting next week, because every week will change. All right, so we are going to find experimental probability of a compound event. So compound event means that we are going to do two or more of something. So if you remember in 4.2, we did simple events, and that was either flipping a coin or rolling a dice, or what else did we do? Picking a card. So those are called simple events because we're only doing one. Compound event means we're going to do two. So for example, I'm going to flip a coin and then I'm going to roll a dice. And then we see what the probability are of getting, for example, a heads and a 1, and a heads and a 2, and a heads and a 3. So those are called compound events. So as you can see on the Spark Your Learning, it says Felix was attending an awards dinner and the menu had the choices shown: appetizer and an entree. What is the sample space for the dinner selection? All right, so for dinner we have two choices. We have an appetizer and an entree. Okay, we have two possible appetizers, and that would either be shrimp or a salad. And then we have three possible entrees. So beef, roast beef, right? Chicken or lasagna. So those are our choices. So our sample space is what are our chances of getting each appetizer and entree. So I could do shrimp, with roast beef. I can do shrimp with chicken. I can do shrimp with lasagna. Okay? And then I can repeat it, but now with a salad. So I can do a salad and roast beef, a salad and chicken, and a salad and lasagna. Okay? So my outcomes are 1, 2, 3, 4, 5, 6. So I have 6 outcomes. So that is the possible outcomes that I can get. Okay? The Turn and Talk says the menu also had a choice of 2 drinks. When considering that choice, how does that affect the total number of combinations that are available to order. All right, so think about it. And I'm just going to do the first one, right? So if I have shrimp and roast beef, I can also have drink number 1, or I can have shrimp and roast beef and drink number 2. So what happens is when we add a drink, we are actually doubling or adding 2 more things to this. So what effect does it have? It doubles the outcomes. So that's what happens. It doubles the outcomes. And the way to figure out your outcomes, guys, from a compound event is you take what I have. So I have 2 here. I have 3 here. And you multiply them. So 2 times 3 is 6. When I add another possibility, I just multiply it again. So 2 times 3 is 6, times 2 is 12. So that will tell you how many possible outcomes we can have. Okay? All right, if you need more time, let me know. I'm going to move on. But if you need more time, put it in. If I can get to the chat. Let's see if my chat's working now. All right, so let's look at this compound event. Okay, Hillary said she needed more time, so let me go back. All right, good. All right, so the next compound event has to deal with colored shirts in different sizes. Okay? So it says Felix Awards Dinner. T-shirts were being handed out to award winners. The choices for the shirts are shown. The selection of a shirt is a compound event due to the available choices in different categories. So it says, how many colors are there? So I know you can't see it on here, but here it's red, blue, and green. And then we have small, medium, and large. Okay? So red, blue, green. So those are my choices. And then the sizes are small, medium, and large. All right, so our outcomes, remember, if we have 3 and 3 here, we multiply it, so I should have 9 possible outcomes. Okay, and those possible outcomes would be a red small, so I'm just going to abbreviate them, a red medium, a red large, a blue small, blue medium, blue large, green small, green medium, green large. So that would be what your combinations are. All right. So now we're going to kind of put it in a table. So what would that look like if we created a table? So I'm going to put red, blue, and green here, and then small, medium, and large there. Now, it didn't matter. I could have put red, blue, green here, small, medium, large. It didn't matter. Okay, because we would still get the same combinations. All right, so we would have a red small, a red medium, and a red large, blue small, blue medium, blue large, green small, that was a horrible G, green medium, and green large. So that's what it would look like in a table. All right, so it says, suppose a compound event includes two simple events. Explain how many rows and how many columns are needed in a table of the sample space. All right, so then the number of rows is equal to the number of choices. And it's the same thing for columns. And the number of columns should equal the number of choices. So, because that's kind of what we did here, right? So this is a simple event. What's the choice of getting a small? Well, it would be 1 out of 3. This is a simple event. What's the choice of getting a red? 1 out of 3. But when we put them together, it's considered to be a compound event. All right? And then the turn and talk goes back to what I said up here. It says, does it matter whether sizes or colors are listed in the rows or the columns? Remember I said it didn't matter. I could put small, medium, large here, red, blue, green here. Doesn't matter. We're always going to have 9 outcomes. So no, because we will still have 9 outcomes. So no matter what I put there, we are still going to have small red, small whatever it is. All right, so let me pause for a second so those people can copy and write. All right, let me know if you need more time. Hillary, you good? All right, I'm not hearing from Hillary. All right, so here we go. Let's look at this one. So now we're going to go back to our whatever you want to call it, bell ringer, bell work, whatever it was called. So it says conduct a survey. Conducting a survey is a type of an experiment. Each time a question is asked of one person counts as one trial. Each answer is an outcome. Compare the number of times one answer is given to the total number of times a question is asked to find the experimental probability that a new randomly chosen person, if asked, will give this answer. So now we're going to experiment, right? So we're going to ask people what they want. So the guests at the awards were asked for their dinner order. The number of people who gave each answer are shown. Find the experimental probability that a dinner guest will have roast beef and a salad. All right, so the first thing we need to do is, how many people did they survey? Well, we're going to need to add 15, 32, 12, 24, 22, 15 together. When I add that, I get 120. So they surveyed 120 people. So then what you do is you say, okay, I'm going to go look for roast beef and a salad. How many people chose that? So roast beef, salad. So that would be 24. So 24 out of 120 is the experimental probability. And then if it can be reduced, then we reduce it. So let me see, will 24 go into 120? So 120 divided by 24 is exactly 5. Yep. So I would divide each one of these by 24, and I would get 1/5. And 1/5, I know, as a percent, is 20%. And as a decimal, it's 0.20. So 20% of the people asked for roast beef and a garden salad. All right, so now we're going to find that experimental probability of t-shirts. So the t-shirt choices of some award winners were shown in the table. What is the experimental probability that an award winner does not select a medium green? So the easiest thing to do is tell me what is medium green and then subtract it. Okay? So I need to add all this up. So 4, 2, 3, 8, 5, 4, 8, 7, and 9. So I'm going to add all that up. And they surveyed 50 people. Okay? So that's what we're going to put here as my denominator. So we want the number of people who have medium green shirts. So that is 5. So we know that that simplifies to 1/10, which is 10%. But remember, the question said not. So not green. So we want the complement. So the complement is the opposite of green shirts. So if green shirts is 1/10 and the whole thing is 1, or we can say 10 over 10, right? We would subtract 1/10 from 10 over 10 to give me 9/10. So we know that is 90%. So they have a 90% probability that they will not select a medium green t-shirt. So that is how you find experimental probability. Okay, so I'll leave it there for just a minute. All right. Let's look at one more experimental probability. So it says a party bundle sold by an event planning company contains party favors and table decorations. So that's what we have. The party favor choices are keychains, pens, wristbands. So that's 3 choices right there. The table decorations are flowers and candles. So that's only 2. So 3 times 2 is 6. So we're only going to have 6 outcomes. Okay? So they want us to list it. So I'm just going to abbreviate so we can get a key, and a flower, or we can get a keychain and a candle. I can get a pen and a flower, or a pen and a candle. Right? And then the last one is a wristband. So I can get a wristband and a flower, or a wristband and a candle. So if you look, 1, 2, 3, 4, 5, 6. So 6 outcomes. Just what I said up here. 3 times 2, 6 possible outcomes. All right. So now we want to know what made up that compound event. Well, party favors and table decorations. So that's what our event is made up of. Party favor, table decorations. All right, so remember we talked about simulations, and we said that sometimes we're not going to be able to go out and go buy wristbands and pens and keychains and flowers and candles to kind of know what the experimental probability is. But we can use cubes or coins or random number generators to figure out what is the experimental probability. So that's what they're asking you here. How can you use a number cube and a coin to simulate the experiment? Okay? So since we have 2 possible outcomes for key, what I would do is I would let numbers 1 and 2 be the keychain. Numbers 3 and 4 would be the pen, and 5 and 6 would be the wristband. And then the coin, heads would be flower, and tails would be candle. So you would roll the dice and flip the coin to see what comes up. All right, so Tatiana did the experiment for us. So they did 100 trials, and this is what they got. So 21 times people got a keychain and a flower. 18 times someone got a keychain and a candle. 19 times was a pen and a flower. 14 was a pen and a candle. So on and so forth. We want to know what is the probability of getting a pen and a candle. So pen, candle. So 14 out of 100. So since it's already out of 100, I know that we have a 14% probability. If I reduce the fraction, if I divide by 2, I get 70 over 50. So we have a 14% probability or experiment that you'll get a pen and a candle. All right, check understanding, that's where we're at. So take 5 minutes to work on the check understanding, and we will come back and check it. Okay? So 5 minutes. 2.5 minutes. All right, so let's look at this. It says, how many possible outcomes are there in the sample space? So remember, 3 times 2. So we would have 6 outcomes. So it says, what is the experimental probability that a new customer orders buttered white toast? So the first thing we got to do is add them all up. 20 plus 32 plus 8 plus 7 plus 10 plus 3. So they surveyed 80 people, and 32 said they wanted buttered white toast. Okay, so I could divide it by 2 and take half. And that gives me 16 over 40. And I could divide it again. So that gives me 8 over 20. And I can do it one more time, which is 4 over 10. So we know that that is 40%. Okay? All right, so you guys still have about 12 minutes. So if you guys want to start on your own, you are more than welcome to do that. But I do not think it is assigned, so let me look.